Welcome to this coding walkthrough. Today, we'll explore LeetCode problem number 1443, minimum time to collect all apples in a tree. This problem challenges us to work with tree structures and optimize traversal. Let's dive into the details and solve it step by step. This problem involves an undirected tree with n vertices, numbered from 0 to n1. The tree consists of n1 edges connecting the vertices, and the root of the tree is always vertex 0. Each vertex may or may not contain an apple, which is represented by a Boolean array called hasApple. If hasApple I is true, it means vertex I contains an apple, otherwise, it does not. Additionally, the tree structure is described using an array called edges, where each element, a_i, b_i, represents an undirected edge between vertices a_i and b_i. Your task is to determine the minimum time, in seconds, needed to collect all the apples in the tree. Starting from the root, you can traverse the edges in either direction, and each edge traversal takes exactly 1 second. The expected output for this problem is a single integer representing the minimum time required to collect all the apples. Let's look at an example to better understand the problem. In the first example, we are given n equals 7, with the edges forming the tree structure as 0, 1, 0, 2, 1, 4, 1, 5, 2, 3, 2, 6. The hasApple array is false, false, true, false, true, true, false, meaning vertices 2, 4, and 5 contain apples. The output for this example is 8, which represents the minimum time needed to collect all the apples. To understand why the output is 8, we can visualize the tree structure. The tree has vertex 0 as the root, with 2 main branches. Apples are located at vertices 2, 4, and 5. To collect all the apples, we start from the root. First, we take the path from 0 to 2, which takes 2 seconds, and collect the apple at vertex 2. Then, we return to the root and move to vertex 1, from where we proceed to vertex 4, taking 4 seconds to collect the apple there. Finally, we move from vertex 4 to vertex 5, taking an additional 2 seconds to collect the apple at vertex 5. Adding up all these times, the total time required is 8 seconds. In the second example, the tree structure remains the same, but the hasApple array changes to false, false, true, false, false, true, false. Here, only vertices 2 and 5 contain apples. The minimum time required to collect all the apples is 6. Starting at the root, we first go to vertex 2 in 2 seconds and collect the apple there. Then, we return to the root and proceed to vertex 1, from where we move to vertex 5, taking 4 seconds to collect the apple. This gives a total time of 6 seconds. In the third example, the tree is smaller, with n equals 4 and edges 0, 2, 0, 3, 1, 2. The hasApple array is false, true, false, false, meaning the only apple is located at vertex 1. Visualizing the tree, vertex 0 is the root, and vertex 1 is a leaf node connected through vertex 2. To collect the apple, we start from the root, go to vertex 2, and then to vertex 1, taking 2 seconds. After collecting the apple, we return to the root in another 2 seconds. The total time required is 4 seconds. The problem comes with several constraints and edge cases to consider. The number of vertices, n, can range from 1 to 10⁵, and the tree structure is always valid. The edges array contains n1 pairs, where each pair represents a connection between 2 vertices. The hasApple array has a length of n, with each element being either true or false. In terms of edge cases, if there are no apples in the tree, the output should be 0 since no traversal is needed. If all vertices have apples, the output will reflect the total time required to traverse the tree and return to the root. For a single vertex tree, the output is always 0 because there are no edges to traverse. Sparse or highly unbalanced trees should still be handled efficiently, even for the upper limit of n. These considerations ensure the solution is robust and performs well across different scenarios. To solve the problem of finding the minimum time to collect all apples in a tree, we need to evaluate different approaches for traversing the tree structure efficiently. The first approach we consider is a brute force depth first search, or DFS, without optimization. The intuition here is straightforward. Starting from the root node, we recursively traverse all paths to the tree's children, keeping track of the time it takes to reach each apple. If a path leads to an apple, we accumulate the traversal time for that path. The advantage of this approach is its simplicity, as it processes each node and edge exactly once, leading to a time complexity of O(n). However, the major drawback lies in its inefficiency. It doesn't eliminate unnecessary paths. For example, if a subtree doesn't contain an apple, we still traverse it and count those edges, which leads to redundant computations. The space complexity is also O(n), as the recursion stack grows linearly in the worst case, such as in a skew tree. This lack of optimization makes the brute force approach less appealing for minimizing traversal time. A more efficient solution is the optimized DFS approach, which addresses the inefficiencies of the brute force method. Instead of exploring all edges blindly, we can prune paths that do not lead to apples. The key idea is to use a post-ordered DFS traversal, where we process all the children of a node before the node itself. During this traversal, if a node or any of its children contains an apple, we include the time for traversing the edge between the node and its parent. The steps to implement this approach are methodical. First, we build the tree as an adjacency list from the given edges. Then, starting from the root node, we perform a post-ordered DFS, recursively calculating the time required for each child. Whenever a child leads to an apple, we add 2 to the total time, 1 for the edge to the child and 1 for the return. At the end, we return the accumulated traversal time for the entire tree. This approach processes each node and edge only once, maintaining an O(n) time complexity. The space complexity is also O(n) for the recursion stack and adjacency list. The main advantage of this method is its ability to prune unnecessary edges, directly minimizing the traversal time. Another approach we could consider is breadth-first search, or BFS. Unlike DFS, which explores paths deeply before moving to the next, BFS traverses the tree level by level. The intuition here is to track nodes that lead to apples while summing up the traversal time for these paths. To implement BFS, we first build the tree as an adjacency list. Then, using a queue, we process nodes in breadth-first order, keeping track of visited nodes to avoid revisiting. For each node leading to an apple, we accumulate the time for the path and include it in the result. While BFS has the same O(n) time complexity as DFS, as it visits each node and edge exactly once, it requires additional bookkeeping to track visited nodes. The space complexity is also O(n) due to the adjacency list in queue, which can grow with the size of the tree. However, BFS can feel less intuitive for tree traversal compared to DFS, and it lacks the natural pruning mechanism that DFS provides, which can make it less efficient overall for this specific problem. Ultimately, the optimized DFS approach emerges as the best strategy for solving this problem. Its efficiency lies in its pruning mechanism, which ensures that only paths leading to apples, or passing through apples, are included in the result. By using a post-order traversal, we process subtrees first and only include their traversal costs if necessary, directly minimizing the total time. This approach aligns well with the tree structure and leverages recursion to simplify the implementation. While BFS is a valid alternative, it involves more overhead due to explicit bookkeeping and does not provide the same natural pruning as DFS. The brute force DFS, on the other hand, is computationally wasteful, as it fails to exclude unnecessary paths, leading to redundant calculations. In summary, the optimized DFS strikes the ideal balance between efficiency and simplicity, making it the most effective choice for minimizing traversal time in this problem. It avoids unnecessary computations while maintaining clarity in implementation, which is crucial when working with tree-based problems. In this problem, we are given a tree with n nodes, where nodes are numbered from 0 to n1, and there are n1 edges connecting them. Some nodes contain apples, and our goal is to calculate the minimum time required to collect all these apples, starting from the root node, which is node 0. Each edge traversal costs 1 unit of time, and since trees are acyclic, there's a unique path between any two nodes. To solve this problem efficiently, we use depth-first search, or DFS, with some specific optimizations. The first step is to represent the tree as an adjacency list. The edges are provided as pairs, U, V, where each pair represents an undirected edge between nodes U and V. Using this information, we construct an adjacency list. This structure helps us easily access all neighbors of a node, which is critical for efficient traversal. Once the adjacency list is ready, we can start traversing the tree using DFS. The traversal begins at the root node, node 0. To avoid revisiting nodes or creating infinite loops, we maintain a visited set. For each child node of the current node, we recursively call DFS, but only if the child hasn't been visited yet. This ensures we explore the tree systematically, one branch at a time. Now, as we process each node during DFS, the next step is to check whether the current node or any of its descendants contains an apple. If any of them do, we need to account for the time required to traverse the edge to this child node and return back. This traversal adds 2 units of time for a round trip. However, if a branch of the tree contains no apples, we can completely disregard the time for traversing that branch. This optimization ensures that we only include necessary edges in our total time calculation. Using this approach, we minimize the total time required to collect all apples while still ensuring that we explore all relevant parts of the tree. The recursive nature of DFS makes it well suited for this problem because it allows us to naturally check all paths and prune unnecessary branches at each step. Additionally, to prevent redundant computations or cycles, we rely on the visited set, which ensures that each node is processed only once. Together, these elements, recursive DFS, pruning unnecessary branches, and using a visited set allow us to solve the problem efficiently. The adjacency list plays a key role here, as it enables quick traversal to neighboring nodes, making the entire algorithm run in O(n) time complexity. The visited set is also critical for ensuring that nodes we've already processed are not revisited, which avoids redundant computations and keeps the algorithm efficient. Moving on to the complexity analysis, the time complexity is O(n), where n is the number of nodes in the tree. This is because each node and each edge is visited exactly once during the DFS traversal. The space complexity is also O(n), which accounts for the adjacency list used to represent the tree and the recursion stack used during the DFS calls. With the algorithm's logic and complexity clear, let's now look at the implementation. First, we build the adjacency list using the given edges. This involves iterating through the edge list and adding both endpoints of each edge to each other's list of neighbors. Next, we define the DFS function. We start by adding the current node to the visited set and initializing a variable total_time to track the time spent processing the current subtree. Then, for each neighbor of the current node, we check if it hasn't been visited. If not, we recursively call DFS on this neighbor to process its subtree. Within the DFS function, after processing a child node subtree, we check if the subtree contains apples. If the time returned by the child's DFS call is greater than 0, or if the child node itself contains an apple, we add the time spent on the child's subtree plus 2 units for the round trip. This way, only useful edges leading to apples are included in the total time. Once all child nodes are processed, the function returns the total time spent on the current subtree to its parent call. Finally, we initiate the DFS traversal from the root node, node 0, passing in an empty visited set. The function returns the minimum time required to collect all apples. This implementation captures the essence of the algorithm, combining efficient tree traversal with pruning of unnecessary branches to achieve optimal performance. By focusing only on edges that lead to apples, we ensure the solution is both correct and efficient, leveraging the tree structure and the properties of DFS to solve the problem in O(n) time. This Python implementation solves LeetCode problem number 1443, minimum time to collect all apples in a tree using depth-first search (DFS) for traversal. Here is the step-by-step explanation. 1. We start by importing defaultDict from the collections module to construct an adjacency list representation of the tree from the input edges. 2. The minTime function accepts 3 parameters, n, number of nodes, edges, list of edges, and hasApple, a Boolean list indicating whether each node contains an apple. 3. We construct the adjacency list tree using a loop over edges. Each edge connects 2 nodes, so we add both directions to represent the undirected nature of the tree. 4. The core computation lies in the DFS function, which recursively traverses the tree. It takes 2 parameters, node, the current node, and parent, the previous node, to avoid revisiting. 5. Inside the DFS function, we initialize total_time to 0, representing the traversal time required to collect apples from this subtree. We iterate through the children of the current node. If the child is the parent, we skip it to prevent backtracking. For each child, we recursively call DFS to compute the time needed to collect apples in its subtree. If this subtree contains apples or leads to apples, we add the traversal time, 2 units for the round trip. 6. The DFS function returns the total time required for collecting apples from the current node subtree. 7. The main function starts the DFS traversal from the root node, 0, with no parent, -1, and returns the total time calculated by DFS. This solution is efficient, as each node is visited only once, resulting in a time complexity of O(n). The space complexity is also O(n), due to the adjacency list and recursion stack. Here, we start with the Java implementation of the problem. First, we import the necessary libraries and define our solution class. Inside the class, the main method minTime takes 3 parameters: the number of nodes n, a list of edges representing the tree structure, and a list of booleans has apple indicating whether each node contains an apple. The first step in this method is to build an adjacency list to represent the tree. We use a hash map where each node maps to a list of its connected nodes. For each edge in the input, we add connections in both directions to ensure the tree is undirected. Once the adjacency list is constructed, we call the helper method DFS to perform a depth-first search starting from node 0. The DFS function will calculate the total time needed to collect all apples in the tree. In the DFS helper method, we initialize total time to 0. This variable will accumulate the time spent traversing the tree from the current node. We then iterate over all the children of the current node, which are retrieved from the adjacency list. If a child node is the same as the parent, we skip it to prevent revisiting the node we just came from. For each child, we recursively call the DFS method to calculate the time required to collect apples in its subtree. If the subtree time is greater than 0 or the child node itself contains an apple, it means we need to traverse this path. In that case, we add the subtree time plus 2 to account for the round trip to and from the child. Finally, the total time for the current node is returned, which allows the recursion to propagate the accumulated time back up the tree. In this example, we are given a tree with 7 nodes and a list of edges that represent the connections between these nodes. The hasApple array indicates whether each node contains an apple. Our first step is to build the tree structure as an adjacency list. This representation allows us to efficiently traverse the tree and explore parent-child relationships. Here, node 0 is connected to nodes 1 and 2, node 1 is connected to nodes 0, 3, and 4, and so on. This adjacency list will serve as the foundation for our depth-first search, or DFS, which we'll use to calculate the minimum time required to collect all apples in the tree. Using the adjacency list, we perform a DFS starting from the root node, which is node 0. Since node 0 has no parent, we pass -1 as its parent. From node 0, we first explore its child, node 1. At node 1, we further traverse its children. Node 3 does not have an apple, so it contributes no time. However, node 4 does contain an apple, so we add 2 to the total time for the round trip. This gives a cumulative time of 2 for node 1. Next, we explore node 2 from the root. Among its children, node 5 has an apple, contributing 2 to the time, while node 6 does not, so it adds nothing. The total time for node 2 is also 2. Finally, summing up the contributions from nodes 1 and 2, the total time for the root node is 4. This is the minimum time required to collect all apples in this tree. In this example, we have a tree with 4 nodes and no apples on any of them. As before, we start by constructing the adjacency list from the given edges. This structure shows the parent-child relationships between the nodes. Next, we perform a DFS starting from the root node, which is node 0. From node 0, we proceed to its child, node 1. At node 1, we explore its 2 children, nodes 2 and 3. Since neither node contains an apple, they each contribute 0 to the total time. With no apples found in the entire tree, the total time for node 1 remains 0. Returning to the root node, node 0, we see that no time was added from its child node. Since there are no apples anywhere in the tree, the total time for the root node is also 0. Therefore, the minimum time required to collect all apples in this tree is 0. This example highlights that when there are no apples present, no traversal is necessary, and the result is simply 0. In this case, we have a smaller tree with 3 nodes, and every node contains an apple. We begin by building the adjacency list from the edges, which shows the relationships between the nodes. Using this structure, we start a DFS from the root node, node 0. From node 0, we move to its child, node 1, and then proceed to node 1's child, node 2. Since node 2 contains an apple, we add 2 to the total time for the round trip. Returning to node 1, we include the time for node 2, resulting in a total of 4 for node 1. This value is then passed back to the root node. At node 0, the total time to collect all apples is 4. Despite the small size of the tree, the result reflects the need to traverse and return from every node containing an apple. In analyzing the time complexity for this problem, we start with the process of constructing the tree. Since the tree is represented as an adjacency list, we need to iterate through all the edges to build it. A tree with n nodes has exactly n1 edges, so this step requires n time. Next, the depth-first search, or DFS traversal, processes each node exactly once. During this traversal, each edge is visited a maximum of 2 times, once for each endpoint as recursion progresses and backtracks. These operations collectively also take n time. Additional computations within the DFS, such as checking for apples or calculating traversal costs, are constant time operations per node. Summing these steps, the total time complexity for solving this problem is n plus n, which simplifies to n. When considering space complexity, there are 2 main components. First, the adjacency list used to store the tree structure requires space proportional to the number of nodes and edges. Since each of the n1 edges is stored twice, once for each node it connects, the adjacency list consumes n space. Second, the recursive call stack during the DFS depends on the height of the tree. In the best case of a balanced tree, the height is approximately log n. However, in the worst case of a highly skewed tree, the height can reach n. Combining these, the total space complexity is n for the adjacency list plus h for the recursion stack. In the worst case, where the tree is skewed, this results in an overall space complexity of n. Now, analyzing the best, average, and worst cases gives us further insight. In the best case, the tree is balanced, and no apples are present. While the DFS still visits all nodes, no additional traversal time is added, so the time complexity is n, and the space complexity remains n. In the average case, apples are scattered randomly across the tree. Here, traversal time depends on their locations but still adheres to n for both time and space. The worst case occurs with a skewed tree where apples are at the farthest nodes. This forces the recursion stack to reach its maximum depth of n, and traversal still visits all nodes, resulting in n for both time and space. For comparison, a naive approach that repeatedly traverses the tree from the root to each apple would lead to redundant visits, yielding a far less efficient time complexity of k*n, where k is the number of apples. Our DFS-based solution avoids such inefficiencies, ensuring an optimal n time complexity. This solution is highly efficient due to the use of an adjacency list and a single-pass DFS. The adjacency list provides a compact and efficient way to store the tree structure, minimizing memory usage while allowing fast traversal. The DFS ensures that each node and edge is processed only once, avoiding redundant operations and maintaining optimal performance. Mathematically, the time complexity can be summarized as n for tree construction and n for the traversal, leading to a total of n. Similarly, the space complexity includes n for the adjacency list and up to n for the recursion stack in the worst case, resulting in an overall n space complexity. With problem constraints allowing up to 10,000 nodes, this approach remains scalable and efficient, making it an ideal solution for the given problem. One of the most common mistakes in this problem is not accounting for the fact that the edges in the tree are bidirectional. In a tree structure, edges are undirected, meaning you can traverse them in both directions. If you forget this, you might end up with an incomplete depth-first search or, even worse, unintentionally create cycles in your traversal. To prevent this, always use a visited set or a similar mechanism to track nodes you've already processed, ensuring you don't revisit them. Another frequent issue is including unnecessary edges in your calculations. Remember, you only want to count edges that actually lead to apples. If a path doesn't contribute to collecting apples, it shouldn't be part of the total time calculation. Additionally, misunderstanding the return value of your DFS function can lead to errors. If your recursive DFS returns the time spent, make sure you're aggregating results correctly and adding traversal time where necessary. Finally, inefficient graph construction can slow down your solution. For example, using lists instead of adjacency dictionaries can introduce unnecessary overhead during traversal. Always aim for a clear, efficient representation like an adjacency list to make your traversal faster and more intuitive. When solving this problem, it's important to handle edge cases carefully. For instance, consider a tree with no apples at all. In such cases, the result should simply be 0. Similarly, think about trees where all the apples are located in leaf nodes. You'll need to ensure your solution correctly traverses to these nodes and backtracks as needed. Another edge case involves disconnected components, though in well-formed tree inputs, this shouldn't typically occur. From an interview perspective, the key insight here lies in your ability to traverse the tree efficiently, identify useful nodes, and prune irrelevant paths. This pattern of tree pruning is a common theme in many problems, so mastering it will go a long way. Focus on optimizing your solution to count only the edges that contribute to collecting apples. This not only makes your solution correct but also improves its time complexity, a point worth emphasizing to interviewers. Additionally, brush up on graph theory fundamentals, particularly DFS and BFS. While DFS is more intuitive for this problem, being able to discuss both approaches demonstrates flexibility. Lastly, be sure you're comfortable with constructing an adjacency list from an edge list, as this is a routine requirement in many graph problems. This problem is closely related to several other tree and graph problems on LeetCode that can help you strengthen your skills. For instance, LeetCode number 226, Invert Binary Tree, is a good starting point for practicing basic DFS and BFS traversal. LeetCode number 112, Path Sum, challenges you to check tree paths based on conditions, which mirrors the logic of filtering paths in this problem. Another related problem is LeetCode number 863, All Nodes Distance K in Binary Tree, which involves similar traversal techniques combined with distance calculations. Finally, LeetCode number 1376, Time Needed to Inform All Employees, is another time-based tree traversal problem that shares conceptual similarities. Regarding alternative approaches, DFS with pruning is the optimal choice for this problem. It involves recursively traversing the tree and including only edges that lead to apples. This approach is straightforward in logic, but recursion depth can be a concern for very large trees. Alternatively, you can use iterative DFS or BFS. These methods involve using an explicit stack or queue for traversal, which eliminates recursion depth issues. However, you'll need to carefully manage bookkeeping to ensure you're including only the relevant edges in the total time calculation. Another approach you can consider is bottom-up dynamic programming. This technique involves treating the tree as a rooted structure and calculating the time required to collect apples by working upwards from the leaves. Starting from the bottom ensures that you aggregate the cumulative time needed for each subtree before moving to the parent nodes, which aligns well with problems requiring cumulative aggregation. However, this approach is more complex to implement compared to straightforward DFS or BFS. It's particularly useful if you're dealing with problems where you need to process information from child nodes before making decisions at the parent level. While the trade-off is increased implementation complexity, it's a powerful technique to have in your toolkit for more advanced tree-related problems. Great job! We've covered the solution for LeetCode problem number 1443, which involved optimizing tree traversal using DFS. Remember to practice similar problems to build a strong foundation in recursion and graph algorithms. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!